isotropic lines. In the two-dimensional case, that is where the phase space is two-dimensional, this group is called SP2R and is exactly the same as SL2R, which is 2 by 2 real matrices with determinant equal to +1. Another notion that we would use very often later on, particularly when we move on to discrete phase spaces, is the notion of a foliation of the phase space. Now, take each isotropic line, a line through the origin, and construct sets of lines which cover the entire phase space and are parallel to this given isotropic line. This then you have a decomposition of the phase space into a set of lines parallel to the chosen isotropic lines. So in the context that we are dealing with at the moment, a few, 2 or 3 isotropic, 2 or 3 foliations or striations are indicated in these figures. Of course, we would have one such foliation of the phase space for each isotropic line. Now, these are certain concepts which I would use, but they're not very difficult to remember, and I hope you keep them in mind. Now, given a phase space distribution, FQP, we can associate with each line a probability by integrating FQP along that line and hence obtain a marginal distribution corresponding to each such foliation. Thus, for the first 2 foliations, we have, you just take that FQP, integrate it over P prime, you will get a probability distribution and which is pointwise positive and integrates to 1. Similarly, for the second foliation, you get another probability distribution. So with each foliation, you can, given a probability distribution over the phase space, you can associate what are called these marginal probability distributions. Now we pass to, this is again very standard, and I'm sure that you must have learned in basic courses in quantum mechanics. One of the earliest methods of passing from classical mechanics to quantum mechanics is to associate a Hilbert space with our system and elevate the classical variables Q and P to operators Q hat and P hat on this Hilbert space, and the Poisson bracket of the phase space description in classical mechanics goes over to the commutator Q hat P hat is equal to IH cross times the identity. So this is the prescription for passing from a classical description. Again, we are restricting ourselves entirely to Cartesian situations where the coordinate space we are dealing with is Cartesian. Now, this is a prescription which takes us, which associates with Q and P operators, Q hat and P hat. But what about some arbitrary function of Q and P? And this problem becomes particularly important because now the operators Q hat and P hat do not commute with each other. And therefore, we have to now, in order to make connection between the classical description and quantum description for any arbitrary function, phase space function, we need a prescription. Now I will quickly review 3 of the many possible such prescriptions, which go by the name Wigner-Weil prescription, normal ordering prescription, and anti-normal ordering prescription, each of which has its own importance and significance. And later, in the later part, when we move on to discrete phase spaces, we will entirely restrict ourselves to the Wigner-Weil description, or we will seek analogs of the Wigner-Weil description available in the discrete case. Remember that whatever we have just said does not apply to the case where Q and P are discrete variables, because Q hat, P hat equal to IH cross in a finite dimensional on a finite dimensional Hilbert space does not make sense, because the left hand side trace is 0, but the right hand side trace will be something finite. So it won't. This prescription applies strictly to the case where Q and the associated momentum operator both are Cartesian. Any questions up to this point? All right. If not, then we proceed to the next slide. Now, before passing on to these prescriptions, I will, just to set the notation, I will recapitulate things which you already know. Position operator, its eigenstates, the coordinate eigenstates. Then we have the momentum operator, whose eigenstates are labeled by P taking values -infinity to +infinity, and the properties, they form an orthogonal set in the Dirac sense, and the overlap between Q and P states is familiar 1/√2 pi e to the IQP. Now, out of these Q's and P's, we can also construct some useful operators called creation, annihilation, and creation operators, and which are the sort of complex linear combinations of Q hat and P hat, and particularly this operator, the annihilation operator, is important because its eigenstates lead us to the notion of coherent states, as you all know, labeled by a complex number Z. The coherent states are non-orthogonal, but they give you a resolution of the identity and therefore constitute an overcomplete set. Then you have an operator, Hermitian operator N, which is A dagger A. And as you all know, the eigenstates are labeled by discrete index N, taking values 0, 1, 2. They form an orthonormal set and give you a resolution of the identity in this way. The coherent states that we introduced earlier can be expressed in terms of these number states in this manner. Now we come to some operators which will be very crucial in the phase-space description. These are called Weil operators. I have given their properties here, and I would not go through them, but I would suggest that whatever properties I have indicated here, you sit down and prove them for yourselves. There's some typos here. There should be a V here, for instance, VQ dagger VQ equal to identity. So now I have listed them for completeness. I'm not going to, I'm sure that most of you are familiar with it or can derive it very easily. Out of these operators, we can construct a displacement operator, which is one of the most crucial operators that we would need for our purposes later on. Now, the properties of this displacement operator are composition, unitarity, orthogonality here, and their action on Q0 and P0, eigenstates of position and momentum operators, is to shift the Q0 by a certain amount, multiplied by a phase factor, which is given here. And this phase factor is very crucial, as we would see later on. Again, remember that in this composition, dqp, dq prime, p prime, we have here e to the I by 2, and there's a 2 appearing here. And just keep that in mind. Later on in discrete, in the context of discrete phase spaces, we will find that in some cases division by 2 is not permitted, and therefore one has to be a bit more careful in using and defining the composition between these displacement operators. So please, I would urge all of you to go through these properties that I have listed here and derive them for yourselves. Again, it proves convenient to rewrite all these properties in terms of A's and A daggers, which are linear combinations of Q's and P's, and I have put them together in the form in terms of Z and in terms of Z. Of course, remember that these are functions of both Z and Z star, but for compactness of notation, we do not include Z star as an argument. And the coherent states that we introduced earlier are related to the number state corresponding to n equal to 0 by the action of this displacement operator. Now, let me ask you a question. Whatever I have summarized in these slides, have you all gone through it at some stage, or is this entirely new to you? Hello? No response anyway. So let me proceed further. Now we come to the first.
We are able to hear. Subhash, we are able to hear, no problem.
Now we come to the first of these ordering prescriptions, which is called while or symmetric ordering. Here also, again, I will sketch the ideas, and you can then check them for yourselves. And if there are any typographical errors, you can at some stage bring them to my attention. So this is what I expect from you after you've gone through these slides. Now the while rule is you start with the exponential function of Q and P as given here, with lambda and mu are some parameters taking values from -infinity to +infinity. And the rule is that now you replace these Q's and P's by the operator, non-commuting operators, Q's and Q hats and P hats. Or in other words, this exponential function of Q and P goes over to this displacement operator d mu lambda on the phase space. Now, by equating like powers of lambda and mu on both sides, we can find what are the operators associated with any monomial q to the n, p to the n, as per this prescription. Thus, for instance, qp will go to 1 by 2 q hat p hat, p hat q hat, q squared p squared will go to this operator. It's called symmetric ordering, but remember that it is a special kind of symmetrization induced by the correspondence that we have given here. For example, q squared p squared is q times q p p. It does not mean that we include all possible orderings of q's and p's, symmetrize this monomial, but it is done in a specific way dictated by this ordering rule. And as I said, for any given monomial, we can find the corresponding operator by equating like powers of lambda and mu. Now, once we have this prescription for the exponential, we can extend it to any arbitrary function of FQP through Fourier transformation. And let me just quickly outline the steps. So let me denote by F tilde lambda mu the Fourier transform of FQP. So this is the relation between FQP and the Fourier transform. QP will go to an operator where this exponential will get replaced by the displacement operator. Now, substituting for F tilde mu again into this equation, we obtain this, and thereby a procedure to associate with any phase space function an operator FW hat on the Hilbert space. So this is the procedure for going from an operator on the phase space to from a phase space function to an operator on the Hilbert space. This can again be rewritten, and this f hat then can be expressed in this form, which is an integral over the phase space of that given phase space function times this operator, which again we would come back to several times in due course of these lectures, and which is referred to a phase point operator. So this is an operator associated with each phase point. So now you can appreciate that the crux of this entire construction is in this phase point operator, which can then be used to convert any phase space function into an operator in this Hilbert space. Now, using the orthogonality, trace orthogonality of dqp, we can invert this relation to go from an operator to its phase space function. So this is the whole idea. This is the whole strategy, and I will come to the summary of this prescription. So the Wigner-Weil prescription is as follows. Given an operator A, and given these phase point operators as defined above, we can pass from this operator to a phase space function WQP. Conversely, given a phase space function, we can pass to its operator in this manner. Now notice that the same phase point operator is involved in going from the operator to its phase space function and conversely. All right. Now some of the properties of these phase point operators are given here. These are Hermitian operators, trace one, and satisfy this trace orthogonality condition. In contrast, so the two operators that are going to play a very important role in whatever we do hereafter are the displacement operators, which are unitary operators, and trace orthogonal. The phase point operators, on the other hand, are Hermitian operators, trace one, and these are also trace orthogonal. I have rewritten these statements in terms of Z and Z star obtained by complex combinations of Q and P's, which are also somewhat useful. I would again urge you to make sure, check these statements that are made here. Nothing much except for a change of variables from Q and P to the corresponding quantity Z and Z star. Now we come to the second prescription, which is called the normal ordering prescription. Now, we start with this exponential function, rewrite it in terms of these variables here as defined. Now, still at this stage, these are still classical variables. So this exponential can be broken up in this form. And after we have done that, we elevate the combinations of Q and the A and A star to operators in this manner. So this is this particular prescription. Again, as before, by following the same method, equating like powers of lambda and mu on both sides, any monomial and Q and P, you have the corresponding operator acting on the Hilbert space. This rule is called normal ordering because you notice that on the right-hand side, the operators always appear in a form in which A daggers appear to the left of the A's, and therefore it is called a normal ordering rule. So in a nutshell, what it means is that e to the I lambda q I mu p goes to the displacement operator multiplied by this quantity e to the 1/4 lambda squared plus mu squared, which was, of course, absent in the Wigner-Weil description. And it is this factor which distinguishes one phase-space description to the another and has the, one can now again go through similar exercise as before, and then the final picture that emerges is as follows. Given a phase-space function, you pass from that phase-space function to its associated operator within this prescription by calculating this quantity where phi hat is an operator which is given here. If you now want to go from an operator to its phase-space function, you need a different operator Q hat, and the two operators are defined here. So notice that unlike the Wigner-Weil prescription, where going from the phase-space function to its operator, you need one operator Q. In the reverse way, you need another operator, which is indicated here. So it's not symmetric in that sense, in the method, the way in which you pass from the phase space function to its operator, and from an operator to its phase space function. This is the crucial difference between this normal ordering prescription and the Wigner-Weil prescription. Of course, we will see later on that each of these prescriptions has its advantages and have been used very fruitfully in applications in quantum information theory. Yes, so this is same thing rewritten in terms of Z and Z star, and you can check these calculations. Now, here I must point out that this operator Q hat Z, which I had introduced earlier, which is used in going from an operator to its phase space function, essentially turns out to be a projector on coherent states. There's a typo here. The bracket should be pointing the other way around. Anyway, I'll correct it later on. And as a result, given an operator A, its phase space function is simply the expectation value of that operator in the coherent states. And this has a consequence that if A is a positive operator, then this QA hat is a positive function of Q and P, as we will see later on. Now we move on to antinormal ordering prescription, or what is called the Sudarshan phi function. Here again we proceed exactly as before, except rewrite this exponential the other way around, so that when we elevate A and A star to operators A hat and A hat dagger, the annihilation operators appear to the left of the creation operators. This is called the normal ordering rule, which in terms of the exponential function of Q and P reads in this way. Now we have a displacement operator times an exponential with a minus sign compared to what we had in the context of normal ordering rule. Now again, proceed exactly as before, and we again get a prescription to pass from a phase space function to its operator, and for that you need this operator Q hat, and to go from an operator to its phase space function, you need this operator phi hat. So again, like the normal ordering prescription, this rule is again not symmetric insofar as passage from phase space function to its operator is concerned, and the other way around. Again, you can rewrite it in terms of Z and Z star, and these are reproduced here. Now, as we noticed earlier, that since Q hat Z is this projector onto the coherent states, we obtain for any operator A what is referred to as the diagonal representation of Sudarshan. That is to say, any operator can be expressed in terms of these projectors ZZ onto coherent states multiplied by a function phi AZ. All right. So this is a consequence. This is an outcome of the anti-normal ordering prescription, and this particular expression of any operator, in particular for the density operator, is referred to as the diagonal representation of Sudarshan. All right. So now, as an immediate consequence of this is that if your phase space function you are dealing with is a positive pointwise positive function, then this rule associates with it a positive operator on the Hilbert space. Now let me give you some comparison between the three prescriptions. All the three prescriptions associate real phase space functions with Hermitian operators, and conversely, real phase space functions with Hermitian operators. All of them relate quantum averages with respect to the density operator to the moments of the corresponding phase space distributions in a simple and well-defined manner. In the normal ordering prescription, the phase space function, the Q function associated with a positive operator is pointwise positive. The converse is not true in general. In the antinormal ordering prescription of Sudarshan, the operator associated with a positive phase space function is a positive operator. The converse is not generally true. Now, you would expect that in the Wigner case, we would have the best of both the worlds, namely a positive operator would go to a positive phase space function, and a positive phase space function would lead to a positive operator is not fulfilled, and one finds that the Wigner description fails on both counts. There's no guarantee that a positive operator maps to a positive phase space function, and a positive phase space function maps to a positive operator. However, one great virtue of the Wigner description that it is autonomous. All you need is the corresponding phase space operators as defined by this prescription, which enable you to go one way and the reverse way as well. Whereas the antinormal ordering and the normal ordering functions involve two sets of operators, and therefore the procedure is not symmetric. Another feature that sets Wigner-Weil description apart from the other two is that as with the classical phase space distributions, its marginal distributions are genuine probability distributions. That is, if I have a system, I have the density operator, I construct the corresponding Wigner function, and I integrate this Wigner function, which is not necessarily a probability distribution, but it's marginal distributions. That is, if I integrate it along lines in the phase space, what I get is a genuine probability distribution. Another feature which sets Wigner-Weil description apart from the other two is the property called traciality, which I come to in a minute. And that states, there's some mix up in my slides, which states that trace of a product of two operators is then the phase space average of their corresponding phase space functions. Whereas in the other ordering prescriptions, this is not true. You would require one kind of phase space function for one operator, other kind of phase space function or the other operator. So in that respect, a Wigner function is autonomous in the sense that I've just mentioned. So now, what do we mean by Wigner description? Let me just quickly summarize that. In quantum mechanics, we have a Hilbert space. A state is defined by a positive operator with trace 1. Phase space descriptions proceeds by associating with each phase point sigma a phase point operator W sigma, which can be used to transcribe the given density operator into its Wigner distribution. W sigmas are trace orthogonal permission operators. They have this marginous property, that is, when added along a line in the phase space, yield a projector. The projectors belonging to the same foliation are orthogonal to each other in the delta function sense, and those belonging to different foliations are mutually unbiased. Displacement by amount sigma 0 in the classical phase space is implemented by displacement operators d sigma 0 at the Hilbert space level. Symplectic transformations S at the phase space level go over to unitary operators US at the Hilbert space level. The phase point operators are covariant under symplectic transformations. So this is the crux or the kind of requirements that we need in order to say that we have a Wigner while or a Wigner description for a given system. Any questions at this stage? Yes? Any questions? All right, no question, then we now go further.
Subhash, there are some problems with unmuting, so that is the reason, they are probably having a problem. So आप proceed कीजिए, मैं उनको बोलता हूँ, उनको बाद में allow करने के लिए ठीक time पे.
अच्छा अच्छा. तो हाँ ठीक है, फिर आखिरी में I will if there are any questions we can discuss them in the last half hour. All right. Okay. Now let me list some of the useful applications or new ideas that arise from whatever we have discussed so far. First of all, the diagonal phase space, diagonal representation of Sudarshan has been used to define, at least in quantum optics, what is meant by non-classical states. So this is one notion that arises from these phase space descriptions that we just discussed. Then they also allow us to define the notion of Gaussian states, namely those states rho for which the corresponding Wigner function is Gaussian in the variables Q and P. So they lead to the notion of Gaussian states. Then we have the notion of Gaussian channels. Those channels, those operations on rho hat, which take a Gaussian state to a Gaussian state. So these are two very important notions that arise from these space considerations. Notion of a Gaussian state, notion of a Gaussian channel, because at least in quantum information applications, there's a lot of work done on Gaussian states and characterization of Gaussian channels and so on. It has played an important role in complete characterization of two-mode Gaussian states. Remember that the Gaussian is completely specified by its variance matrix. So a Gaussian state is completely specified by its the variance matrix associated with its Wigner distribution, and this possibility makes it possible for us to give a complete characterization of two-mode Gaussian states, entanglement to two-mode Gaussian states, as was done in Simon's work. It has led to definition of UN invariant criterion for multimode squeezing, non-classical properties, characterization, various kinds of non-classicalities. And historically, another important application has been transcriptions of quantum master equations into Fokker-Planck type equations, and then pass on from the Fokker-Planck type equations to the corresponding Langevin equations. The advantage is that now these are C number equations, and you can, if you cannot solve them exactly, you can solve them numerically by putting them on a computer. So for instance, if I have a master equation of this kind for the density operator, which describes dissipative motion of a quantum oscillator, which was developed by G.S. Agrawal in this paper. Using the phase space description, it translates into an equation which has a structure of a Fokker-Planck equation, which is given here. That you have a drift and a diffusion. So it has a structure of a diffusion equation, and from which you can pass on to corresponding Langevin equations, which are written here. And these can be, if you wish, in more complicated problems, they can be simulated on a computer, and you can get some information about the quantum averages by solving these equations. Now, let me just also indicate some recent work that I've done with Professor Agrawal. This facility to pass from the master equation to a classical Fokker-Planck equation to the corresponding Langevin equation was put to great use in the description of Brownian quantum Brownian heat engines, in particular in identifying what could be the definition of work done and heat produced in a quantum context. So this is done in this paper. So if you're interested, you can look it up. Now, once again, let me, now hereafter we will focus only on the Wigner description, and let me give a summary of what we have done. Given an operator A hat, we can associate with it a Wigner distribution. The Wigner distribution can also be obtained from this A hat by this formula, which I would like you to leave it as an exercise for you to prove from the formula that I had given earlier. If A is real, this Wigner distribution is also real. If A is Hermitian, then the corresponding phase space description is leads to a real function. The marginus property, average of the Wigner distribution corresponding to a state rho hat along a line in phase space yields a probability density. And then the most important property, which is traciality, which is trace of A hat, B hat, is given by the phase space average of the corresponding phase space distributions. All right, just one more statement. For pure states in Hilbert space, the Wigner distribution is positive if and only if the state is a Gaussian state. So for pure states, we have a result that only those states which are Gaussian states, that is whose Wigner distribution is a Gaussian, are such that their Wigner distribution is a positive, is a genuine probability distribution. Now I will quickly outline another approach to Wigner distributions. Remember that what we have done so far is through ordering prescriptions of various kinds, and we arrived at, in particular, the symmetric ordering prescription led us to the Wigner function with the properties that I have listed earlier. I will now outline another approach which we have developed, which I refer to as Dirac-inspired square root approach to Wigner distributions, which, as you will see, comes in very handy in the context of discrete phase spaces. Because in discrete phase spaces, we no longer have Q hat and P hat, which are operators obeying the commutation relations, Q hat, P hat commutator equal to IH cross. So that entire framework is not available anymore. And in order to do this, one needs an alternative approach. And this is what we have been able to do, as I will indicate in the following, in the next 10 minutes. So here the starting point is this traciality property. Now you notice that the left-hand side is symmetric under interchange of A and B, whereas the right-hand side isn't. So now we ask the question in a typical Diracian fashion, whether we can make the right-hand side also manifestly symmetric in A and B through some suitable manipulations. This can indeed be done, and I would skip the intermediate steps for you to work out. And what one can do is to show that this right-hand side can also be expressed in this manner by using completeness relations at appropriate stages, and where AQP is defined in this manner. It is the expectation value of A hat. It is the A hat sandwiched between QP multiplied by overlap of P and Q. And this kernel KPQ is given here. All right. Now, at the expense of introducing this kernel, what we have achieved is that the right-hand side also becomes manifestly symmetric under interchange of A and B like the left-hand side. Next, what we do is to this kernel that I've written down, as you can check, is symmetric under QP going to Q prime P prime. So what we do is to essentially define the square root of this K and absorb part of it, the square root on one side and the remaining one on the other side. That is what we are looking for is a function psi, which is given here. This should be P double prime, sorry, P double prime semicolon. I will make those corrections, which is also symmetric in its two arguments, that is QP going to Q prime P prime. So this, we look for a symmetric square root of this kernel KQP. Indeed, this can be done, and details may be found in our paper. Then eventually what we get is that we can write trace AB as a phase space average of functions associated with the operators A's and B's, and these functions are, this function is given here. A little algebra then shows that AQP is precisely the function that one associates in the Wigner description. So what we have done is we have arrived at the Wigner description purely in an algebraic manner by finding the symmetric square root of a certain kernel. So we call it a Dirac-inspired approach because this is a kind of question which Dirac would have asked by looking at the expression for the trace to make the right-hand side symmetric under a interchange of A and B like the left-hand side. And in this process, what we are led to is a completely algebraic way of arriving at the Wigner function description. And this becomes important when we go to discrete case, in which this kernel would be simply a matrix of appropriate dimensions, and all we would need is to find a symmetric square root of that matrix. So it becomes a completely algebraic problem. Any questions? No problem so far? No question. Okay, I will proceed further. So I have tried to indicate to you that starting from the traciality property of the Wigner distribution and requiring that the right-hand side also be a symmetric function of the phase space functions that appear therein, we are led automatically to the Wigner description in a purely algebraic manner. Here I'm just indicating that what happens when our configuration space is not the real line. Then, for example, if you consider a particle on a circle in the classical context, then what will be the corresponding phase space description? As I said earlier, that in the classical case, there's a standard procedure to go from the configuration space to the phase space. In quantum mechanics, this ceases to be so, and one has to define what is meant by a phase space in the quantum context. So here I'm just indicating to you some work that we have done in the context of configuration spaces, which are group manifold of a compact Lie group. And this work is not entirely an academic exercise because, for instance, if you look at a classical system like a rigid body, then its coordinates are take values in the rotation group, and then you may ask, what is the possible way of giving a phase space description to such a system? The effort that we have made in this direction is summarized in these papers, which you can look at in case you are interested. Now we come to phase space description of discrete quantum systems. Again, here I am only going to sketch to you the ideas underlying passage to description of finite state quantum systems, because there are certain concepts and certain mathematical structures which most of us in physics are not generally familiar. When we go to discrete spaces, first question we ask is, what is meant by a coordinate? What is a coordinate? And normally you would say, okay, I can, if I have a three-state system, I will say that the coordinate takes values 0, 1, 2, 3 values. And correspondingly, I will postulate a coordinate basis and then define a momentum basis through a finite Fourier transform. Now, all this becomes, you have to now, you are confronted with a situation where you have to decide what kind of an algebraic structure one should choose for the Q's and P's. Whether Q's and P's take values in a field, which is only available in prime power dimensions, or QP take values in the what is called a ring and is denoted by ZPN. This decision has to be made because in each case, the phase space, the structure of the phase space, the geometrical properties of the phase space are completely different. So, of course, when the dimension is of your finite state quantum system is a prime number, then of course both the description coincide, because then FP is same as ZP. So this is the first problem that one is confronted with. And here I have tried to give you some sort of all right, I will attend to them now. Please. The question is, I can't hear you. So I will read out the question. Can we move from finite dimensional Hilbert space to Wigner distribution formalism? This is a good question. I had done some work in the reverse way, that is passing from the continuum to the discrete case. There's some unpublished work in this, because my aim was to define notion of Gaussian states in the discrete context. But there are several mathematical questions which I've not been able to answer. I'm working at it, but this is all that I have in what happens is, what one finds is that in this work, what I showed was the analog of the Gaussian states in the continuum are described by theta functions, Jacobi theta functions. There is a lot of work that remains to be done, which I certainly would, if time and energy permits, I would like to pursue. So I have nothing more to say on this.
Sir, may I ask one small follow-up question? I am Ritaprata here. Yeah. So this theta function means the theta function which we generally typically do for the special function theory or in the number theory. This is the same thing you got for the Gaussian states there also, right?
Yes.
That is very fantastic. I mean, I like to talk to you. Any case, let us complete the thing and then I'll ask you some other questions later.
What I want to do is, this the theta function that we get for Gaussians. Anyway, I think I'll discuss it with you separately.
Sure, sir. Definitely.
Thank you. And if you're a young man, if you can make some progress in that direction, I'll be very happy. Okay. Yes. Yes, please. Is this written here? Can spin operators have a corresponding Wigner distribution? My question is, can a finite dimensional operator have a Wigner distribution which is continuous in nature? The answer is, the phase space associated with a finite dimensional system would necessarily be, labeled by phase Q's and P's, which are take discrete values. So, answer to your question, to the best of my knowledge, is let me qualify this by saying that we have a certain notion, Wigner functions. You have to first define a phase space, and then there are certain properties that you would like to associate with the phase point operators. And that is what I call a Wigner function. Of course, you can associate continuous variables which are discrete systems by, for instance, in the context of spin systems that you talk about, you could take expectation values of that operator in the what are called spin coherent states, which are functions on a sphere. So, but this will not have, when we speak of a Wigner function, there are a lot of other structures that are associated with it. notion of a marginal distribution, notion of product of trace of operators being expressed in terms of the corresponding phase space functions, and so on. So certainly what you say is possible, but it is not in the spirit with which Wigner description is carried out. All right, now I move on to why Gaussian states are so important for quantum systems physically, and can we attain that much temperature in reality to attain these states experimentally? Now, Gaussian states are important because an important class of quantum states, because they are completely characterized by their variance matrix. And therefore, otherwise, if you take an arbitrary state, quantum state, there is no such object that will completely characterize that state. So Gaussian states are important in that sense. Now, can we attain that much temperature in reality to assign these states experimentally? Well, basically, a Gaussian state is a mixed state, and the temperature is just a parameter that appears in that description. So it's just that if you can prepare a suitable incoherent mixture of states with appropriate weight functions, then you have a Gaussian state. So I do not know. Maybe I don't appreciate your question that well. We will come back to your question at the end. Okay. Can we discuss with systems in quantum phase space formalism? Yes, and as an example, I will discuss a qubit or a two-stage quantum system at the end. All right, no further questions. So let me now proceed. So again, in view of the questions that were asked, I would like to clarify that when we speak of a Wigner description, there's a certain setup that is required in order to say that now this is a Wigner phase space description. You have to have a phase space, you have to have the notion of lines on this phase space, foliations, then notion of marginal distributions, and so on. So that is what we would like to do now. The first case in which, now let me say that it suffices for any arbitrary dimension. It suffices to study phase space descriptions in which Q and P take values in the finite field P to the n or take values in a ring. All right, because by the fundamental theorem, any n can be, any integer can be expressed as a product of primes, so prime powers. So it suffices to restrict to one or the other. Now the difference between the two approaches is the following. Let me just indicate, because we may not have much time. This first case was discussed by Wouters et al. In a very famous paper, Waters and Fields. I'm sure that those of you who are interested in these matters have gone through it. And here we have a phase space where Q and P take values in the finite field. So it will be a sort of a lattice, the basic phase space. Of course, the advantage of working with this finite field, which is discussed in detail in Gibbons and Waters' paper here, is that you have all the properties. This phase space has all the properties that you have in the continuum case. That is the case when your Q's and P take real values. So there we were working with a real field, and you have all the geometrical properties of a field. Namely, in this phase space, 2 points define a line. Parallel lines have no points in common. Any two non-parallel lines intersect at exactly 1 point. As a result, the phase space has exactly d+1 isotropic lines or straight lines through the origin, and hence each isotropic line gives rise to d-1 lines parallel to it, and therefore generate a striation of the phase space. Decomposition of the d-squared phase points constituting the phase space into d lines containing d points each. Each isotropic line may therefore be chosen as a representative of the corresponding striation, and therefore we have d+1 striations for a given system. D, remember, is P prime power. Now, for technical reasons, one restricts oneself to odd prime powers. Special care has to be taken when P is equal to 2. These are matters of detail, and it's really not possible to cover. It would require one full lecture on this Waters and description in the finite case. Any two non-parallel lines intersect at exactly 1 point, and therefore there are exactly d+1 lines through a given phase point. So these are, in particular, two lines intersect at two non-parallel lines intersect at 1 point is very important. This, as we would see, does not happen when the phase points are described. Q's and P's take values in a ring. So here is a picture, for example, of P equal to 3, in which case both the ring as well as the field coincide. Here, this is a phase space, which is a 3 by 3 lattice. This is one straight line, isotropic line, another isotropic line, another isotropic line here, and another isotropic line here. And these are the corresponding striations indicated here. Lines which are parallel to this line. They may not look parallel because of the fact that these are, we are dealing with fields, but they are parallel in the sense that this line, which is indicated, for example, with these stars, is obtained by shifting this by an amount, by a displacement in this direction. All right. So d equal to 3, you would have 4 striations, which are 4 isotropic lines and 4 corresponding striations, which I have illustrated here. Let me now indicate to you the strategy of arriving at a phase space descriptions through the work of Wouters and our approach. Now what happens is that here you've got 4 d squared minus d plus 1, sorry. Here in this case, let me go back a bit. I'm sure that all of you must have at some stage come across mutually unbiased bases. So mutually unbiased bases means in d dimensions, what you are looking for is d plus 1 sets of orthonormal bases such that the scalar product of any vector from one of them with the scalar product with any vector from any other one is given by 1 over square root of d. These are called mutually unbiased bases. These are available in prime power dimensions. Now, Wouters' work, what it does is makes use of this information to associate with each striation a mutually unbiased basis. So let me indicate that in the context of a qubit, a very simple example. So this is our phase space, and this is 2-dimensional. So we have 3 mutually unbiased bases, which are given here. You can see that this is an orthonormal basis. Each one of them is an orthonormal basis, and the scalar product of any vector from one basis with any other vector squared, modular squared, is 1 over 2. So with each striation, you associate a mutually unbiased basis. Now, each striation, you have a corresponding isotropic line. You associate a projector corresponding to some vector in this mutually unbiased basis to that line. Then associate the vectors to the other lines in that striation by the application of the displacement operator. All right. So this is what you do. So once you have done that, you would have ended up associating a projector with each line in on this lattice. Such a collection is called a quantum net. Such a description is quantum net. So we associate projectors to each of these lines, making use of the availability of mutually unbiased bases in prime power dimensions. Then we can construct the phase point operators by summing. You take a point, and the phase point operator at that point is given by adding up the projectors associated with the lines passing through that point minus I. That gives you the phase point operator associated with that point in the phase space. So this is the overall construction, but relies heavily on the availability of mutually unbiased bases, which are then used to associate projectors with the lines in the phase space, and through that one constructs the phase point operators. And then, of course, there are many possibilities. The way you make the association of the mutually unbiased bases with the striations and assign projectors to the isotropic line in that striation, and so on. So that is the in summary, striation, you associate a mutually unbiased basis. To each isotropic line, you associate a projector corresponding to that mutually unbiased basis vector. Associate vectors with the other lines consistent with the displacement. So you apply a displacement operator of the requisite amount to go from the isotropic line to a line parallel to it. This is the construction. Of course, the way you assign the mutually unbiased bases you will in general have d into d plus 1 possible quantum nets. Not all of them would be similar. Not all of them will be essentially different. They may be related to each other by the Clifford group, which I mentioned earlier. So one needs to find out how many of them are actually independent. This requires us to study the orbits under this Clifford group, and I will not go any further, but to refer you to a work that we had done earlier, which is this spectra phase point operators in odd prime dimensions and the extended Clifford group, essentially to find out how many essentially different phase space descriptions are possible. So let me repeat. When we go from in the continuum, there is, for the situation that we dealt with, there's only one Wigner description. But when we go to the discrete case, there are several equally good Wigner descriptions. Now we can, depending on the application that we have in mind, we can choose which one suits our requirements best. This could be, for instance, the eigenvalues of the phase point operators, that they should be, the spacing between the eigenvalues should be large or they should be closely spaced. You can choose the corresponding Wigner function description. Now we come to Z to the Pn. The structure in this phase space is somewhat more complicated. The number of isotropic lines, the formula for the number of isotropic lines, given a phase point, what are the isotropic lines, what are the lines passing, number of lines passing through that point, then intersections and the orbits under the Clifford group in this context. They are quite complex and are summarized in this paper in JPhase phase A. Those of you who are interested can read this. But here, the basic strategy is to construct the phase point operators first by following that square root approach. All right. And then construct the projectors. what one finds is that yeah, so I will just not spend more time on it. Those of you who are interested in this can read this paper and get back to me in case you have any questions. So let me just, in one case, the author's description relies heavily on the availability of mutually unbiased spaces. Our description, based on the symmetric square root, applies both to the field as well as the ring case. All you have to do is to find the symmetric square root of that matrix that comes in. In both cases, you have many possible Wigner descriptions, and one can choose which one is the best for your applications. For example, in some work on quantum coding, you might choose a Wigner function in which the eigenvalues are as widely spaced as possible. Anyway, let me not go into that. So I think with that, I will come to an end. I have also included, for those of you who are not familiar with finite free fields, some elementary notes on finite free fields, the way I learned them, and there's some further work on the projectors that can be constructed using our approach, because in the ring case, you have many more lines and therefore many more projectors, and therefore one can ask the question whether one can construct out of them a suitable for tomography purposes. This question is addressed in a recent paper with Subhash, K.R. Parsarthi, and Ajit Iqbal. I think I will stop here and take questions. Hello? I think the best thing would be if you post it on the chat box. Where is the chat?
That you have to unmute and
What do I have to do? Chat, yes.
So if there are no more questions. Yeah, if there are no more questions, then we can conclude this session today for now.
May I just add one question, because there is nothing
yes,
from the
please.
student side
Yes,
so far. Yeah. Sir, I just wanted to know, since you have pointed out for the finite field and the Wigner distribution there,
Yes.
do you get something interesting if you go for, let us say, an infinite field and then you define the Gaussian states, for instance, there in it? I mean, finite field, I understand that you have connected with the things like your unextendable product basis and so on and so forth. But in case of the infinite dimensional situation, let's take the L2 of some infinite thing, let's say real. So do we get something interesting for the Gaussian states or structures?
Yeah, I didn't understand your question. This is very annoying echo. I don't know from both sides. When I speak, I get my voice back. And now, can you write that question, please?
Okay, let me just write it here. I don't know. Yeah, it has gone.
Yes. What happens for Gaussian states or channels in infinite mode scenario? In the continuous case?
Yeah.
In the continuous case, these have been quite well studied by Mukunda, Simon, and also Gaussian channels by Krishna, Subhapati, Simon.
But sir, that is on the finite modes. I am asking about infinite modes. The number of mode is infinite.
Oh, yeah. I do not know much work on that subject because, again, entanglement in the context of what we know is two-mode case, but multi-mode case, what are the necessary and sufficient? Certainly a very, very interesting question in its own right. And multi-mode situation, there are many, many questions which still remain unanswered. And certainly they will be very interesting.
Actually, there was a recent paper, actually not so recent actually. This Rajaram Bhatt and his students actually worked out.
Yes.
This is on the structure of the Gaussian states for infinite modes actually. But and what they showed is that it is something like a Hilbert-Smith operator plus identity in this form. So you know that CCR relation actually comes in that format actually. There is a Hilbert-Smith plus some identity operator. But I actually am searching for some place where I can actually see them in physics where it has been used. So that's why I thought of asking you this question.
I must say I've been somewhat out of touch with these things for a long time. So I will think about it if something comes to my mind.
Maybe I'll talk to you later on this thing, or maybe send you a mail. Yeah, that is it. Thank you very much, sir. Thank you. Very nice stuff.
All right. Okay. So Prashant. So I can say goodbye to all of you.
Yes, sir.
I do not know. It was certainly a very quick review of Wigner functions in discrete and continuous case. And as I said, the discrete case, it requires a lot of preparation before one can discuss it. But I think I've given you some flavor for what is involved. And perhaps you can, on your own, study later on if your research work requires sort of deeper understanding of phase-space description of finite state systems. I think with that I will say goodbye to you all, and thanks for your patience of sitting through such a long. Okay, thank you very much. All right, bye bye.